apps, what we have covered DNS, UDP, HTTP, TCP, and in continuation of that, we have next lab assignment, which is based on IP datagram and few questions based on ARP. So we know that in protocol stack, when we are going to transfer a data from one machine to another machine, and data created at application layer, and it traverses downwards the layers, then each layer appends its header to the data part, and uh, the whole, including the header of the upper layer, the lower layer considers it a data, and when it comes to the lower layer again append its own header. The same process happen in each and every layer in the protocol stack. So this is the way how data transfer from uh, application to, and one application to another application. So let me share my screen. In that scenario, we are going to discuss what is IP header format, uh, the network layer append its header, and what are the information available in the IP header. So my screen is visible. All of you can see the IP header format.
Yes, sir.
Yes, sir.
Okay, so before that, this is the head. What you can see. This is IP datagram header format. So whatever the data we cover received from transport layer, network layer append its header. So you can see the data part. That is the part which is coming from transport layer. This one, this part is coming from the transport layer, and this header length is included. This header is included at network layer, and the details about the header, what are the information are there, are given below. So like version, header length, services. So before that, I want to tell you something that uh, IP makes best effort delivery to attempt each and every datagram, but it does not guarantee it. It does not guarantee that each and every packet will be delivered, and we know that uh, we have some limitations of the transferring a packet from one source to destination. Like we have, if we have a medium which can transfer a data of specific bytes only, like in case of Ethernet, we can transfer only 1500 bytes. We have another medium which is having which has been transfer capability of 500 byte. In that case, we need to do the fragmentation of packets to transfer from source to destination. So in that case, we need some fields which can be included in the header part, so that we can identify that how this fragmentation has been done, how to reassemble the data at the destination. So these are the fields which makes an important role to make the do the identifying the fragmentation, how to reassemble the packets. These all can be done with the information which are available in the header format. So in case of IP header, what we can see, the first part is version, which is a 4-bit field that identifies which IPv version we are being currently using. Like we are using IPv4 or IPv6. So this field mention when we will open Wireshark, then you will see what are the information. All the information are there, and the next part that will be length. A length is again a 4-bit field containing the length of IP header in 32-bit increments. The next is service. We sometimes we also call it type of service. Which type of service is using? Then the total length, considering the length of IP packets, that includes the IP header and the user data. So whenever we are going to find out that how many data we are transferring in a segment, then what we do, we just remove uh, decrement the IP header and we get the data part, that how many data we are transferring. This is the total length including the IP header. Then second field in the second row, the field are identification, flags, and fragment offset. So this I will explain through this example, like identification field and flags and fragments. So these are the fields which are used to. I was telling that if we are going to transfer a packet from source to destination, and the situation is that we are creating more fragment. Like we cannot transfer a packet as a whole, so we need to create fragment. Then some information are there, like identification field to identify that the packets, these packets are belongs to the uh, these fragments are belongs to the same packets. So that is for identification field. And then three flags are there. If you can see in IP header, three flags are there, which is 3-bit information. So in that case, uh, 1 bit is reserved. The second bit is don't fragment bit, and next is more fragment bit. So and another is fragment offset. Fragment offset is used to identify that which fragment will set where. Like if fragment offset is 0, then we can say that this is the fragment of uh, first fragmented packet. Maybe we are creating more than one fragment. So if fragment offset is 0, and then we can identify that this fragment is the first fragment. And if down fragment bit is set as 0, then what we can say, fragmentation can be there, or fragmentation is allowed. If don't fragment bit is set to 1, then we can say that fragmentation is not allowed, meaning we can say that there are no fragments. The packet has been uh, transferred as a whole, uh, like the size of the packet is minimum. The next part is most fragment bit. In case of most fragment, if most fragment is set as 0, then we can say uh, this is the last fragment. And if most fragment is more fragment is 1, then we can say the more fragment is there. So this will be clear with this example. Um, Example is we have a 300 bytes packet, and we have including 3000 bytes packet. So here we have 2980 bytes data and 20 bytes header. And we have a network router. The data has come through the router, and we are going to transfer the data to the network. But the limitation is that the link has capacity of transferring only 500 bytes. So in that case, what we do, we need to do fragmentation. And in case of 500 byte, if you are going to transfer in fragments, each fragment will be containing the headers. So header is of size 20 bytes, minimum size is 20. In that case, what we can see, the 3000 data can be sent in segment for 7 fragments. So what we can see here, if the fragment 1 is what we will transfer, we will transfer 480 bytes plus 20 bytes header. 480 bytes will be transfer, 500 we can transfer, so 480 will be data and 20 will be header. So first fragment will be then, and more fragment will be set to 1. Like, meaning if more fragment bit is set to 1, then we can say that this uh, some more fragments are there for the same data. In next fragment, what we will do, we will again transfer 480 bytes plus 20 bytes header, and we can set the fragment offset here. Like fragment offset is 0 for first packet, and This is the fragment offset for second packet. Fragment offset of second packet shows that how many packets has been already transferred. Here we have done the scaling factor, so I am writing 60. So in general terms, if I will say, the fragment offset said that how many bits or bytes has been already transferred in previous fragments. So in this way, we can identify that how many fragments are there. If we continue doing this, once we can see that most fragment bit is set as 0. In that case, what we can say, this is the last fragment, and fragments offset will be set according to the that will be the I think size of whatever the data we have transferred. We'll come to the once we will open everything in Wireshark, everything will be clear. So this is the way that how we can identify that where to fit the packet, like fragment one having the offset value, fragment one having the offset at 0. Then we will put this fragment in the beginning. Then fragment two will be having the minimum value less than, and then fragment three offset value will decide that we will put it on uh, continuation of a previous fragment. So fragment offset is used to decide where to fit the fragment, and count fragment and most fragment bits are used to identify that how many fragments are there, how uh, some fragments are there or not, fragmentation is allowed or not. So I will come to the header part. Then time to leave field. Time to leave field is used to, in case of pack, transferring a packet from source to destination. If time to leave fields, I will say we can consider that how many routers, how many hops it can travel. Like if we have a time to leave value as 4, then each time the packet transfer from one source to another source, like if you have a source and destination, multiple hops will be there, and each hops, when the packet transfer from one hop to another hop, the TTL value will be decreased. So in that case, we decide a TTL value for a packet to minimize the traffic in the network, because if there will be no TTL value and packet will be keep moving inside the network, then there will be a lot of traffic within the network. So once we decide the TTL value, and within the TTL that packet does not reach to the destination, in that case, what will happen? The packet will be dropped. So we can minimize the network traffic. Like we have decided that in 64 hop, the source and destination can be reached, and in 64 hop, if each hop, when the network, when the packet travels from one hop to another hop, the TTL value will get decreased, and if it reached within the defined TTL value, then it will reach to the destination, else the packet will be dropped. Then the protocol field, whatever the protocol is used on the upper layer. Then again, header checksum is used uh, to identify that there can be error in headers or not. There is no concept of checking the errors in data part. So here we have the header checksum. We are considering, we are doing this for header only. You will learn the concept of pseudo IP header when sir will teach you in the class. Then again, source IP address, from where we are sending the data, and the destination IP address. And some options already there, so they have reserved for future use. So I will come to the Wireshark and then I will show you. See, this is your assignment of IP. So, okay. So ICMP is used at a by IP datagram, right? There is no concept of error control in the IP datagram. So ICMP is used for that. So when we are going to these questions are based on it IP at real trace one. So I'm going to open the Wireshark. Okay, I have opened ICMP IP ethereal trace 1. Select the first ICMP echo request message sent by your computer and expect the computer. So I will apply a filter ICMP, and what we can see, the first ICMP echo request is packet number 8. So I will click on this, and we can see what are the information are there. See, there is version. So version field, which is saying that which IPv version we are currently using. Next field is header length. The header length, we told you that header length is 20 bytes. Header is appended with all the IP datagrams. Then total length is 84. So if someone is asking that how many data we are transferring, so we need to remove the size of header length from the total length. Then we can tell that how much data we are transferring within this packet. These are the flag fits, which I have already shown that there is a this is reserved, which is used for which is for future use. Then this bit is don't fragment bit. Uh, do not fragment bit, and this bit is more fragment bit. So we can identify that there is fragmentation or not, how many fragmentation are there, and fragment offset is 0. We can say that fragment offset is 0, meaning this is the first fragment of first fragment, meaning we can say that there are no fragments. So this is the first fragment and packet had been transferred. So we are next field is time to live. Time to live, there is only one. Then the protocol field, which as the protocol is using, that is ICMP. And then we can see the source and destination. The source part is 192.168.1.102, which is the source machine from which this ICMP echo request is generated. And this destination machine 128.59.23.100, for which this echo request is destined. So I will come to the fragmentation part. I think this is in packet number 192. So I will come here. See, I'm expanding the header of this packet number 192. Well, here what we can say, this information is 4. Header length is 20 bytes. Total length is 1500 bytes. This is the data which we are going to transfer through Ethernet, because the total length is 1500 bytes, and the capacity of Ethernet is 1500 bytes. So if someone asks that how much data we are going to transfer, in that case, what we will do, we can reduce the size of header, like 1500 minus 20. So 1480 bytes we are going to transfer uh, through this segment. And then what we can see in this bit is reserved, and dot fragment base is 0, and 1 more fragments are set to 1. If more fragment is set to 1, meaning what we can say, there are more segments are there. More segments are there. We'll come to see reassembled in 193. So what we can see, 1500 bytes transferred from this serial packet number 192. If I will come to the 193, what see, 20 bytes header, and again 548 bytes total length, meaning we are using Ethernet, but still we are transferring 548 bit, because the total size is around maybe around 2000. So 1500 bytes and 548. So again 20 bytes header included in 548. Here what we can see, these are all 0. Fragment offset is 1480. So what we can see in the first fragment, fragment fragment offset can be calculated for the next fragment, that how much data has been already transferred. So we can see that in frame number 192, we are transferring data of 1500 bytes. So 1500 bytes, including the header size also involved. We have transferred 1.8, so 1480 bytes we have transferred, and 20 bytes is header. So the fragment offset value for the next fragment, which has been fragmented in 193, we can see in Wireshark. So fragment offset value will be 1480 for second fragment. And if more fragment bit is set to 0, in that case we can say this is the last fragment. Here I have shown, if more fragment bit, more fragment bit is set to 0, in that case we can say this is the last segment. So in our Wireshark we can see this is more fragment bit is set to 0. In that case we can say this is last segment. And here what we can see, two IPv4 fragments of 2008 bytes. So there was a message which site was 2008 bytes, and we have transferred through Ethernet in two frames. So frame number 192, frame number 193. So payload, we can say that 0 to 1479 has been transferred in frame number 192. As we can see in Wireshark, and the rest of the data, which is 528 bytes, has been transferred through another fragment. See, we can fragment count, and this is the way how we can identify that how many fragments are created for our packets, which is the first fragment, which is the second fragment. I will also come to the some more question. Within the IP packet, what is the value of upper layer protocol field? So using this, we can see uh, which protocol has been used on the upper layer. So we can see it from Wireshark. How many bytes of IP header, how many bytes in the payload? Again, how many bytes in IP header? How many bytes are in payload of the IP datagram? Payload is the thing, meaning how much data we are going to transfer. Payload does not consider the header part. Payload consider the how much data we are transferring. Uh, has this IP data stream has been fragmented? So if we are going to check that this is data is fragmented or not, so we need to observe these 3 bits, the flags which are there. Depending on the situation, that flags are 0 or 1, we can decide that the datagram has been fragmented or not. And this is some instruction that how to sort out, apply filter, and how to sort out your trace. Based on that, you need to given the answer. And then second part is Ethernet part, ARP. So in case of ARP, what we do, actually ARP is generally used to get the MAC address of the machine. If we are within a network and we want to transfer a packet from source to destination, then we all know that in computer network we need 6 identifier, like source port, destination port, source MAC, destination MAC, source IP, and destination IP. If we are going to transfer a packet from source to destination, then destination IP will be known to us, but for transferring a packet, MAC address is also required. In that case, ARP is used. And generally, whenever we are going to get an IP address, get a MAC address of an IP address, then what we generally broadcast an ARP request within the network. And what will happen? We will append that IP address and IP address of source, MAC address of source, IP address of destination, and MAC address of destination will be, we will be uh, asking for the MAC address of the destination. In that case, what we'll do, uh, we will be doing the broadcasting. I'm showing you here. See, this is some trace based on ARP. So what we can see, we are going to transfer a packet, but we don't know we are running an ARP request. So we are going to in ARP request. See, if we will, this is an ARP request hardware type, which hardware we are using, Ethernet protocol type, we are using IPv4. Opcode, opcode means this is a request or response. See, sender MAC address. Some devices are there. This MAC address is mentioned because uh, when we are going to transfer a packet, then we will be the source and we will be able to know what is the MAC address of source. Sender MAC IP address will also be known. Target MAC address is all zero because here we are going doing broadcasting. In case of broadcasting, we have done here mentioned all zero. And target IP address, meaning we are going to get the MAC address of the IP address, which is 192.168.1.1. So see, in the second packet, we are getting the reply. So ARP request is broadcast, but in case of ARP reply, this is unicast. We know that who has made the request for ARP. We have the IP address and MAC address both. In case of ARP reply, in that case, ARP reply will be unicast. So this all information are same. IPv hardware type. You can see the sender MAC address. Now MAC address will be the sender MAC address will be the address MAC address of the machine for which we have made the request. Then IP address uh, to which we have made the request. Then these addresses will be sender addresses, and the target addresses will be uh, from where we get the ARP request. So here we can see embed mic. Some networking device is there which is making we have made the ARP request. That device is now our target, and this is target IP address. So this is the way to how the ARP works. So if we want to know what is the hardware address, then hardware address will be, we can see here also. Center MAC address, we can see in Ethernet frame also. In Ethernet frame also, we can identify what is the IP address. But in case of ARP request, see, all F. All F means we have generally done that. We put all F in case of broadcasting uh, a packet. So ARP request is broadcasted. So destination broadcast in case of broadcast is a 48-bit MAC address. So in place of 48-bit MAC address, we have done all F. So in case of all F, all the packets, all the nodes within the network will receive the ARP request and which match with its IP address. If IP address does not match, it will discard the packet, and the nodes which will to which the IP address will match, it will reply for the ARP request. So this is the way how ARP works. What is the value of Ethernet source address? So this is all about IP datagram and ARP. I have given some idea about how to solve your assignment, and a little bit about the most important thing about the assignment is how to know the fragments, how to know the more fragments are there or not. So once you will analyze the packet, you will able to identify that how to calculate the offset value, how to know that more fragments are there or not, and uh, which packet, how many fragments have been fragmented for a data. Anyone want to ask anything about this IP datagram and this image is clear to everybody or not? IP datagram header format. Okay, so I think we have covered enough to so that you can solve your assignment. So I'm going to post your assignment. If you want to ask anything, we are here.
ठीक है अमित, ज्यादा बताने का जरूरत नहीं है, काफी बता दिया तुमने.
ओके सर.
ठीक है
जी.
इनका असाइनमेंट अपलोड कर दो एंड लेट देम डू. ओके
ओके सर.
ओके
ओके सर.
ठीक है, आई एम लीविंग नाउ.
ओके सर.
हेलो अमित सर.